So in this video, we're going to go over Chapter 9 terms. This has primarily to do with large scale events on the ocean. So things like El Nino and kind of global patterns. So we'll go through a few of those terms today. And if you got any questions, please follow up with me. Okay, so Chapter 9. Acoustical tomography is the way that we use sound, acoustics, to measure different features in the atmosphere. So kind of like we talked about sonar before, same principle with the atmosphere. Antarctic bottom water is a specific mass part of the ocean that is very cold and very dense. So as you recall, when we talked about density of water, the densest type of seawater is cold and salty. That is Antarctic bottom water. That's the coldest, saltiest water on our planet. And so as a result, it tends to be at the very bottom of the ocean. We talked about this a little bit in lecture, Antarctic circumpolar current. It's just a very big name for the current that goes around Antarctica. And what's interesting about this one is there's no barriers to it. And so the current continues to go around Antarctica and it doesn't stop. So because of that, you tend to get very powerful waves and weather because there's nothing for the waves to break against. Cobbling is a unique situation where you have you have different water masses that have different temperatures and salinities, so different densities. But the way it works is because of the mixture, it causes the density to flip. So cobbling is a very specific example, and I don't want you to worry too much about it. But what I do want you to know about cobbling is it's a way just using density to mix water. That's all that is. Coastal upwelling is a very important term I want you all to know. It is the situation where you have water at the coast moving away from shore. And so as it moves away from shore, it's replaced by water from below, right? It wells up, it upwells. This typically occurs in a few places on Earth. We talked about off of California, off of South America are the big ones that I want you to know. There's one in the equator, right? But that's equatorial upwelling. We'll talk about in a minute. So coastal upwelling happens when you have winds blowing in the right direction and you have Ekman transport, which is moving water 90 degrees to the wind. And that allows the deep cold water with all the nutrients to come up. And that's coastal upwelling. Contour current, just a current that follows a contour. Nothing, we're not going to talk much about that in this class. Convergence zone, we've talked a lot about convergence when we were talking about plate tectonics. So we have divergent and convergent. Convergence is a general term for anything that just comes together, right? They converge, they come together. Countercurrent is when you have two currents flowing counter or opposite of each other. So you might have one current going this way and another current going this way, and those are called countercurrents, right? And they mix and they exchange things like heat and gases and nutrients, things like that. A current is in this context, it applies, in this chapter rather, it applies to water, but it can be applied to air, etc. Current is essentially motion of a substance, right? So if you stand outside, you might have a current like a breeze, or if you're in the ocean, you might have a current like, you can feel the water moving by you, right? So current is just kind of a motion of particles. Could be water, could be air. Downwelling Not terribly important. It's just the opposite of upwelling. So instead of bringing up cold, deep, nutrient-rich water, you're doing the opposite. You're pushing it down, right? So you're pushing it away. Eastern boundary current is the opposite of western boundary current. So let's start with western. So a western boundary current, a good example we talked about in class is the Gulf Stream off of the east coast of the United States, the Kuroshio current off of Japan, and the East Australian current off of Australia. They're called western because they're on the western side of that particular ocean basin, right? So if you look at the North Atlantic, on the western side of the North Atlantic is the east coast of the United States. I know there's a lot of directions, right? North, south, east, west here. But when you look at an ocean basin, the western side, that's where the western boundary current is. Western boundary currents are very warm because they're moving from the equator towards the pole. So they're moving a lot of heat. They tend to be very fast. And they're fast because remember we talked about the gyres and how it's not kind of like a symmetrical dome, but it's kind of shifted. And that shift of the dome pushes that current against the landmass. And so what happens is kind of like when you take your finger and you put it over a water hose, right? It goes from flowing a little bit, you put your finger over it to going really fast, right? Western boundary currents are warm, they're fast, and they're also very deep. They tend to be very large, but from the surface, they look very small. But if you look down in the water, they're very deep. The eastern boundary currents are the opposite. They're fairly cold because they're coming from the poles back to the equator. So they're kind of the return of the gyre to the equator. Tend to be very shallow, and they tend to be very broad. And they're just think of them as the opposite of western boundary. An eddy, excuse me, is an eddy is kind of like anytime that you have, it's kind of the way I think about it, a whirlpool. So if you look at kind of Gulf Stream, you can see the stream itself. And then if you look, you see these little like whirlpools kind of off to the side. Those are eddies, right? So they're just kind of these little circular motion of ocean that gets separate. Ekman spiral. Ekman spiral is what happens to the different vectors, right? So remember we talked about the way the wind blows and you have Ekman transport 90 degrees. The Ekman spiral describes what happens to kind of, remember the arrows, the vectors I talked about, how as you go deeper, they turn, right? Because of the 45-degree angle, they kind of turn, so they make a spiral, right? That's why it's called the Ekman spiral. Ekman transport is what happens when you take all those vectors, right? And you add them together to get one vector. So that's where you get the wind going one direction and Ekman transport 90 degrees to the right in the northern hemisphere. You get Ekman transport to the right. Right, so Ekman transport is kind of, if you sum all those arrows up for Ekman spiral. El Nino is, refers to a large-scale weather pattern that is global, but most often it's talked about in the Pacific Ocean, but it really affects the whole planet. It usually happens around December or so, and what happens is it's a shift in it's a shift in the high pressure area in the Pacific Ocean. So what you need to know about this is it's a shift in how the wind and water moves in the Pacific Ocean. And what happens is it has large scale effects. What it does is the upwelling that normally happens off of South America, when El Nino happens, it stops. It goes from upwelling to downwelling. And that's the main thing I want you to know about this. ENSO is related to El Nino. It stands for El Nino Southern Oscillation. I wouldn't worry about ENSO. Just know it's related to El Nino. Equatorial upwelling. We talked about this in class a little bit. This is very similar to coastal upwelling, but it occurs at the equator. So at the equator, you have, in the Pacific especially, you have winds that are blowing across the ocean. And because in the northern hemisphere, things go to the right because of Coriolis, and in the southern hemisphere, they go to the left. What happens is as you have the wind going, the Ekman transport goes away from the center of the wind, right? It goes both directions. So what happens as that moves away, you bring up cold, deep water, right? That's equatorial upwelling. Geostrophic gyre is just, it's essentially that dome of water that happens in the middle of the gyres. And what geostrophic refers to is the balance between the Coriolis force, which is trying to move things to the right in the northern hemisphere, and gravity, which is moving it the other way, right? So geostrophic just refers to Coriolis and gravity, the interaction between the two. Global ocean conveyor belt refers to thermohaline circulation. So let's move forward a little bit for this. So thermohaline circulation is thermo, temperature, and haline is salt. So it's density. So it's essentially circulation in the world's oceans driven by density. That's all it is. Now, what's important about this is about 80% of the volume of the oceans are driven by thermohaline circulation. And so when we talk about moving large amounts of gases and nutrients, thermohaline circulation is really important. And it's all driven by density, which is controlled by temperature and salinity. Okay, so yeah, and so global ocean conveyor belt just refers to the fact that all the oceans kind of move together as a conveyor belt. That's all that is. The Gulf Stream is a western boundary current that occurs off of the east coast of the United States. The one off of Japan, Kuroshio, is very similar in terms of its structure and the way it works. That's about all you need to know about the Gulf Stream. A gyre is a feature that occurs in ocean basins that is typically has four currents, right? So we talked about the western boundary current and the eastern boundary current. You also have one on top and one on bottom. So it creates this kind of, you can think of it like a really big eddy, right? So it's essentially an ocean-sized eddy. And so it's moving the water around, right? And that's what a gyre is. La Nina, we talked about this a little bit with El Nino. La Nina is the opposite of El Nino. What it does is some people call it the normal weather. It's where you have upwelling off of South America. It's also where you have kind of normal weather patterns, right? So if you think about like, when I lived in California during an El Nino year, El Nino, it rained every day in February. It was very, very wet. It just rained all the time because the weather patterns that has shifted over, right? So the high pressure had moved. During La Nina, it was pretty dry. California is very dry in February usually. So you have these kind of large scale global shifts. Langmuir circulation, it's a very specific type of water movement. I wouldn't worry about that. North Atlantic deep water is very similar to Antarctic bottom water, but it's in the North Atlantic. It's also very cold and salty. It tends to form kind of between Nova Scotia and Iceland, so kind of the North Atlantic area. And this is where the cold, salty water forms. And this is the beginning of thermohaline circulation. So when we talk about this in class, the global conveyor belt, it starts, and this is an important thing you'll see on the exam, thermohaline circulation starts at the North Atlantic deep water. Southern Oscillation is part of ENSO. Don't worry about it. Surface current is any current that is at the surface of the ocean. These are typically created by wind, right? Because that's where you get the interaction of the atmosphere and the ocean. Sverdrup, we talked about Sverdrups briefly in class. It's just a measure of volume of water. So when we talk about, instead of saying 2 trillion liters, right, which, what does that even mean, right? It's just some big number. Sverdrup is just another way to take those big numbers and say, instead of 2 trillion, it might be like 12, right? 12 Sverdrups might be like 2 trillion, right? So it's just a different unit to compare volumes. Temperature salinity diagram, we use these a lot to determine the density of water. So you have the temperature on one axis and salinity on the other, and you have these curves, and you can estimate what the density of seawater should be based on temperature and salinity. So, and that drives thermohaline circulation. Transverse current just means a current going across another current, not terribly important. Undercurrent is a current that's under another current. Again, not terribly important. Upwelling, we've already talked about. West wind drift is just another name for the Antarctic. I'm drawing a blank here. The current that goes around the Antarctic, right? It's just another way. I don't know why they put it twice. It's so weird. Western boundary, I already talked about. Westward intensification. We kind of touched on this briefly with regards to western boundary current. We talked about the dome of the gyre being shifted over. And when that does that, it intensifies or makes stronger, right, the western flow. And that's why, the western boundary currents tend to be stronger and faster, right? Wind-induced vertical circulation is just water motion up and down that's caused by wind. Nothing terribly exciting there. Okay, so that's the end of chapter 9. If you got any questions, please let me know.